Welcome back. Last time we discussed about the rectangular microstrip antenna, the fundamental mode of the rectangular patch. We discussed upon the radiating edge, non-radiating edge, and the edges which are contributing to the radiation process. I have mentioned that time the concept of magnetic dipoles. I'll just show you the picture for that, how exactly a magnetic dipole looks like. This is what I mean by that. You apply a formula, M is equal to, this is basically a magnetic dipole directions. You apply a formula where M is equal to minus of N cross E. N is the unit vector perpendicular to the edge. It is the E is the fringing field direction. You calculate the value of M. So if you apply that, this is the dipole orientation which you get. Now this one can design for any arbitrary shaped microstrip antenna depending upon what is the field distribution around the patch for that excited mode. Of course, for more and more complicated structures, the overall picture will look more complex. Okay, number of dipoles probably coming across the edges will increase depending upon the field variations. So for a simple understanding, but again the explanation remains the same. Effective orientation of the dipole directions have to be assessed and calculated for getting the radiation pattern. So here, if you look at these two dipoles along the lengths of the patch, as I mentioned in the earlier lecture, they are anti-parallel and they get cancelled out. Against that, these two are in the same direction, equal magnitude and separated by a distance of half the wavelength, and because of which they add in the broadside direction, right? So this gives me a broadside direction radiation pattern. Now we'll just go one step further and define what is E-plane, because for radiation pattern for a microstrip antenna or any antenna, it is defined in principal planes of radiation. Okay, that is the E-plane and the H-plane. E-plane is the plane which contains the E-plane vector and the direction of maximum radiation, whereas the H-plane is the plane which contains the H-plane vector and the direction of maximum radiation. Because as a layman, when you go to purchase the antenna, you are just interested about what is the horizontal and the vertical pattern of the antenna, or azimuthal and elevation, and that's what you will probably see in the data sheet of the antenna which is purchased. But from the antenna designer point of view, antenna engineer point of view, that is not the way one look at it. One has to go with respect to what are the principal planes of radiation, because that knowledge comes with respect to the resonant modes present. You cannot just define arbitrarily what is E-plane and H-plane. There has to be a process. There has to be a way of understanding where the E-plane is residing. There is, in fact, when we go to the antenna measurements, there we will know how to exactly identify which is E-plane and then what is H-plane. So here, E-plane and H-plane direction is very important. With respect to the resonant mode under consideration, that is TM10, we will define which is E-plane. Now here, as everyone knows, it is a broadside array because two magnetic dipoles separated by a distance of lambda by 2. So the radiation pattern which is going to be coming from the antenna is broadside. Broadside is the direction which is perpendicular to the plane of the antenna. That is called as the broadside. Okay, this is the plane of the antenna. The board plane is the plane of the antenna, and radiation pattern in the direction normal to the board, it is called as the broadside, and it is a broadside radiation pattern. So here E-plane definitely resides in this direction. Okay, in this direction because direction of maximum radiation is here. Now what is the direction of E-plane? E-plane, as I have told you in the earlier lecture, the fringing field direction, it is going down here, it is coming up here because the field is negative, and it is going down there because the field is positive. So the direction of E-plane is this only. So E-plane is vertically directed or normal to the plane or normal to the patch. Direction of maximum radiation is this. So my E-plane is this one. So if I consider this along xy coordinate axis, then xz plane, if I consider length of the patch along x axis, then xz plane becomes my E plane. And naturally, remember, E and H, they are orthogonal always. H plane vectors are in this direction, or they are orthogonal to H plane, E plane, sorry. Thus, if xz is your E plane, yz becomes your H plane of radiation. Okay? Basically, in radiation pattern, first procedure is to identify E plane. H plane is always orthogonal, because consider the case of current carrying wire. If current is going through the wire, the current direction is along the length of the wire. How the magnetic fields are there? They are concentric. So they are always orthogonal. Similarly, you have a magnetic dipole. The magnetic dipole is like this. The electric field will be concentric to the magnetic dipole. So they are always orthogonal. Hence, orthogonal means perpendicular. Hence, if this is my E plane, naturally this becomes my H plane. That is the YZ plane. Okay, that is for fundamental 1-0 mode. If my fundamental 1-0-1 mode is there, that is along this, then this becomes my E plane and this becomes my YH plane. So in that circumstances, YZ plane is my E plane, XZ plane is my H plane. So depending upon where the feed point is there, what is the direction of the E field, you have to identify the plane. How it is done practically, that we will see when we actually go to the antenna measurements topic. Okay, because antenna measurements are to be done for the radiation pattern, for the polarization, for the VSWR or S11, as well as the gain. So there we will discuss in detail what exactly and how to identify this E and H plane specifically for a random or irregular geometries. Because this, and later on also when we go to circular patch, equilateral triangular patch, they are all regular geometries. Okay, for a regular geometries, identification of plane is very simple. Against that, for irregular shape geometries, because in your projects also you may be asked to do some irregular geometries. So how to find out? Because regular geometries are widely explored. Okay, we know the characteristics of those regular geometries. So if you want to work on those microstrip antenna topics related to any of the characteristics like a wide band, narrow band, multi-band, circular polarized, then irregular shape geometries have to be explored. Okay, then you can work and probably publish your work. So for that, knowledge of the irregular shape geometry and how to assess that, that is something very important. Again, that is a advanced part of this topic, especially required from your projects or if you want to publish your work based on your work. So this is how the E and H planes of the rectangular microstrip antenna are defined. Later on, the concept remains same concept will be applicable to the circular patch later as well as the rectangular patch. Okay, so I have given you the magnetic dipole orientation. Similarly, one can draw for all other shapes. So this is what I meant by that. Sorry. This is the broadside radiation pattern. This is E plane and this is H plane. Okay, and these are the cross polar level. Now I will just introduce the concept of cross polar. Remember, this is my E plane of radiation. Okay, now just imagine you have a vertical dipole placed as a receiver, and onto that vertical dipole, if the vertical polarization wave is incident, what will happen? Received signal is always a dot product of the antenna polarization and the polarization of the incoming wave. Now when the two polarizations are matched, then naturally you will get a maximum power. Suppose now if this is the antenna polarization of the receiver antenna and incident wave is orthogonal. Incident wave is orthogonal or perpendicular. What will happen? Dot product is 0. That means your antenna cannot receive any signal from the orthogonally incident wave. Okay, thus cross polar level of your antenna defines your susceptibility of the antenna to receive orthogonal waves. Generally, for a rectangular microstrip patch, okay, under consideration, cross polar level is almost 30 to 40 dB lower than the copolar level. Okay, that much rather attenuation is offered to the orthogonally directed wave by the rectangular patch. Now, cross-polar level is something very important from the practical design. Just consider the design of the antenna required in personal mobile communication or any other wireless application. Can you ensure that if this is the direction of your antenna polarization, can you ensure all the time that receive signal is in the same direction? Not possible. Receive signal polarization is subjected to the travel that signal undergoes, travel path that signal undergoes while going from transmitter to the receiver. There are multiple reflections. Remember, there are multiple reflections. There does not occur a direct line of sight of communication. There cannot be a direct line or drawn between the transmitter and the receiver. And in such circumstances, the signal polarization is bound to change. The signal polarization is bound to change. So because of that, my antenna in practical considerations should be able to receive the signal which is orthogonal to its polarization. So remember, cross-polar level, definitely it is of advantage when you want a purity in the signal. That means what? You only want one directed signal to be received onto it. In fact, later on there are dual polarized antennas, single frequency dual polarized antennas, where I can actually transmit the information in one polarization, another information in another polarization. And if your receiver antenna is like this one, where orthogonal vectors are not going to be received, then it actually enhances the channel capacity. Dual polarizations are used for enhancing the channel capacity. Okay, what do you mean by channel capacity? In the same transmitting channel, multiple information signals can be transmitted. So here, one polarization transmit one signal, another polarization transmit one signal. But that is another case or application. Here, for the antenna under consideration, your cross-polar level is very small. From practical application, this is not so much used. Why? If 1 watt is the received power, just as an example I am telling, 1 watt is the received power when the antenna polarization is aligned, minus 30, or it will be in few dBm, few milliwatts, fraction of milliwatts will be the power when the polarizations are not matched. Then it will lead to a signal loss. But in case of the earlier application where I told you different polarization diversities are required, then cross polar is of the advantage because there is no interference of these two orthogonal waves. One which is directly coming, this will be picked up, this will not be picked up. So cross polar level in simpler terms tells you your susceptibility of the antenna to receive orthogonal signals. Okay, for good antenna it should be as small as possible, but for a practical antenna it should be good cross polar level. In fact, when you go to circular polarized antennas, you will see cross polar and copolar level are nearly equal. Cross polar and copolar level are nearly equal. Of course, that is not only the measure of circular polarization. Circular polarization, even the phase component between the orthogonal vectors should be quadrature. The amplitude should be equal. So, but that is one way of judging whether I am getting close to the circular polarization. So, for the rectangular microstrip antenna under consideration, you have a broadside radiation pattern and cross polar are very small. Another way of looking at this cross polar signal is by looking at the field distribution. Remember, here the magnetic dipoles are oriented. Now we will talk in terms of H-plane wave. If the magnetic vector is incident like this, it will be picked up. Why? Because effective radiation from this antenna is coming from these two edges. But if the magnetic vector is incident like this, will it receive the signal? No. Why? Because these two are cancelling each other. These two are cancelling each other, so it will not be picked up. So, looking at the field distribution on the patch, one can judge what kind of a cross-polar level will be there in the radiation pattern for the given mode. Okay, for the rectangular microstrip antenna in 10 mode, cross-polar level is bound to be very small. Another way of looking at this cross-polar, see, for the rectangular microstrip antenna, I just see whether I have that current distribution. Yeah, I have the current distribution. This is the current distribution direction generated using I3D. Okay, so this is the direct current distribution plot for the rectangular microstrip antenna. Here you will see this is the positive edge or the feed is there, and the currents are directed because positive to negative. So the currents are going to flow from positive to negative. This is a current plot, not a voltage plot. So here what you will see, currents are Jx. Everywhere, since 1-0 mode is there is no field variation taking place along the vertical direction. Currents are unidirectional. There is no Jy part. If there is no Jy part, incident Y field will not be accepted. If on the patch, if you have Jy part by some amount, then definitely you will pick it up somewhere. Now, although I have said Jy part is not there, but some Jy contribution does takes place. From where it comes? It basically comes from the residual contribution of the higher order modes. Right now you can just understand it this way. Although the Jy part in the current is not seen, the Jy part do come from the residual contribution of the orthogonal modes which are higher order. Okay? One example of that I'll just show you is the next higher order mode, PM02. Remember, your rectangular microstrip antenna is excited using a coaxial feed for a 1-0 mode. There is no one can stop you in exciting this 0-2 mode. And definitely it is resonant at high frequency, but of the resonance, some contribution of that currents do remain in the antenna cavity. Maybe 10%, okay, maybe 20%. At the resonance frequency of 1-0 mode. So that residual contribution, just imagine this residual contribution is in some percentage present at 1-0 mode current distribution. What will happen? There will be a Jy component in addition to Jx component, and that is the source of cross polar radiation at lower frequency. And in fact, modified ground plane structures which are called as the defected ground plane structures are used, or even the shorting mechanism has been used in the literature recently for reducing this cross polar, because if I can chop off this higher order mode contribution coming at lower order mode, definitely I can improve my cross polar susceptibility or cross polar level. Minus 30 dB can be brought down to minus 50 dB. Means what? With respect to the copolar level. I hope I have conveyed exactly what exactly a cross polar level is, and cross polar radiation is not at all a disadvantage all the time. It is of the advantage, okay? It is of the advantage, but depending upon the application, that advantages, disadvantages changes, okay? So here I have talked about the radiation pattern of the rectangular microstrip antenna in fundamental mode. Now we'll go to the design procedure. This is something very much important from your exam perspective, okay? Now, I want to design a rectangular microstrip antenna for a given frequency. What are the resonant dimensions which are there? Length and width. As an antenna designer, what you will be given with is the frequency of operation and the dielectric parameters. I will explain the steps now, clearly understand the steps, and then you solve the problem accordingly to realize a rectangular microstrip antenna at a given frequency. Okay, so the problem can be this way: design a rectangular microstrip patch to operate it at 1-0 mode in, say, on FR4 substrate. Okay, dielectric constant 4.3, substrate thickness can be 1.6 mm, and tan delta is 0.02. So at 900 megahertz you design this antenna. So how to go about this? So to start with, what you are given with is the frequency, and you are given with the dielectric constant. Okay, substrate thickness is available to you. C is the velocity of light in free space. Okay, now in these equations which I have written, if you take f0 in gigahertz, okay, if you take f values in gigahertz, and if you mention C as 30, then the dimension you get in centimeter directly. Okay, I repeat, if you take C as 30 and f0 in gigahertz, then you get dimension directly in centimeter. So it somehow simplifies the power of 10 calculations in those examples. Okay, you don't have to worry about what is the power of 10 coming. Directly put these values in those units, you will get the dimensions. Now, what are the parameters to be evaluated? Length and width. But remember, in rectangular microstrip antenna, both the resonant dimensions are possible. Why? Because one can design for 1-0 mode, one can define for 0-1 mode. 1-0 mode deals with length, 0-1 mode deals with width. So, which one is to go for? Here we have 1-0 mode. So, naturally, looking at this dimension you want to find out. This dimension you want to find out, but again, this dimension has a major role to play. I cannot just say with respect to the frequency of operation equate length equal to lambda by 2 and calculate the frequency. Why not? Because width has a lot of role to play. Width is the parameter which decides the fringing field extension for the length of the patch. Means what? See, these are fringing fields. What will be that extent? Whether it will be over this much area or this much area. That is decided by your width of the patch. It is something very similar to a wire. If you have a thicker wire, then amount of fringing from that area will be larger and amount of fringing area will be smaller if you have a thinner wire. Something very similar to that. Here the width of the patch changes the fringing. So to start with, because ultimately remember dielectric constant is given to you, but what happens is these fringing parameters, if you carefully observe, they are going through the air and then to the patch, through the substrate to the ground plane. These components are residing inside the substrate, but these components are going through the air and then terminating onto the ground plane through the substrate. So the fringing field sees two dielectric constants through their passage. One air and dielectric combination and one dielectric combination. And that leads to the concept of effective dielectric constant. Now that effective dielectric constant is a function of width of the patch, because width of the patch that decides your fringing as well as the substrate thickness. And later on it is also a function of frequency, because dispersive effect of the fringing field comes into the picture, especially at high frequency designs. But right now for your course we are just going to concentrate at 900 megahertz or below 2 gigahertz. So we are not going to worry about, and even you are not operating the antenna for a wide band here. If your antenna is a very wide band in nature, then these effects have more roles to play. Okay, because the band of frequency over which your antenna operates is very large. So here you need to have the assessment of the fringing field distribution in view of calculating the width. So what we assume, because ultimately what you are going to find out, length and the width. You are going to find out length and the width. So what you are supposed to do, you have to have some kind of assessment of what will be the fringing. What will be the fringing fields in your rectangular cavity. For that, as an initial estimate, what we say 50% fringing field is going through the air, dielectric and ground plane. That means this component is 50% in nature, who is going through air, through substrate to the ground, and 50% remaining is directly going from patch to the ground through the substrate. This assumption leads to average value of the dielectric constant in the calculation of width. Because why epsilon r plus 1 is the 1 by 2 is done? Because here we are considering average 50-50 contribution of the fringing fields in the patch, in the dielectric. Hence, this is taken as average value. Okay? Hence, this is taken as average value. So, you calculate the width using this equation. That is the first step. Be careful about your units because they are very, very important. Considering the units taken appropriately, considering this equation, first step with respect to our discussion related to the 50% fringing field, calculate width of the patch for a given frequency. Width is calculated, then next step, calculate the effective dielectric constant. Why we are doing that? Because initial assumption was 50%. But now with respect to that width, we need to calculate what is the effective dielectric constant coming because of that passage, air, substrate, ground or substrate, ground. So calculate this using this equation. Okay, remember h is to be taken in centimeter, width is to be taken in centimeter. Then units are balanced. So calculate that. This particular formula is obtained from the transmission line equivalent model of the rectangular microstrip patch. Because one should know from where this formula is coming, is from that. In some cases you may see 12 or 10, but you can use 10H over here. In some books they might have written 12, but that's fine. You can use 10 also, fair bit of accuracy is obtained. Fine. After this is calculated, go to this equation. This is the resonance frequency equation. Again, I am repeating, this is the resonance frequency equation for the rectangular patch operating in TM-MN mode. M stands for number of half wavelength variation along length. That's why this is associated with length. N stands for number of half wavelength variation along width. That's why it is associated with W. Only one correction here. Take this as LE, take this as WE. I have not mentioned this in the slide. Take that L in this equation as LE and W as WE. Okay, so that is the only correction. Now, next step kya hoga? You are for 1-0 mode. Okay, you have to substitute 1 here and 0 here. So you will simplify this equation. Ultimately, this equation will give over here. LE is equal, rather LE will be equal to this equation. Why this equation is obtained? I have put 1 over here, 0 over here. So this part has gone. What I want to evaluate is LE. So I have taken LE on the other side. It gives me this equation. Okay, from here I am going here by rearranging the terms on RHS and LHS. M is substituted as 1. M is substituted as 1. N is substituted as 0. So you get LE. Now what is LE? LE is basically length of the patch plus this fringing extension. Length of the patch with this fringing extension. If you see this, LE is equal to L plus 2 delta L. Delta L is the fringing on either side. Okay. Now there are formulas. There are many empirical formulas are there. We will work on some simple approximation. It works quite well for thinner substrate as well as partial thicker substrates also. So LE delta L, that is the fringing field on one side, is calculated using this equation. Epsilon RE is the value of effective dielectric constant calculated in second step. So after this step you have gone here, then you have gone here, you have substituted 1 0 and rearrange the terms, you have come over here, LE you are going to calculate. Okay, because some of the intermediate steps might be absent in the slide. So I am giving point by point explanation. Okay, so now next you have calculated LE. What you will do using this equation, L is equal to LE minus 2 delta L. What is delta L? Is this. Don't consider this equation right now. Okay, this I have mentioned because if I want to design for 0-1 mode, this will be required. Okay, don't consider this equation at this moment of time. So you have calculated L after subtracting 2 delta L from LE. So you have obtained L. Next step, what is done in microstrip antenna? We consider a rectangular patch to start with, and we consider W is equal to 1.2 times L. We consider W as 1.2 times L. Okay, why? Because the gain of the antenna is required to be higher. Antenna gain, okay, if you go by that aperture area concept, which you will learn in antenna fundamentals, antenna gain is 4 pi AE by lambda square. AE is the effective aperture area of the antenna. Lambda is the operating frequency. Now AE is correlated with the physical dimension of the antenna or physical area. What is that? L cross W. So if W is small, then naturally AE will be smaller there. Okay, and hence as a good practice or as a good designer, we actually take W as 1.2 times L. Okay, you can take 2L also, but there are prices which you pay. There are rather drawbacks of taking W too much larger than L. That I will explain in the next slide. So here, after calculating W, you calculate W nu. Why W nu? Okay, W subscript nu, I should say. Why? Because already one W are calculated in the first step. Remember, this procedure is an iterative procedure. Why iterative procedure? Why? Because in the first equation itself, we have done some approximation. And when you are doing an approximation, there is bound to be an iterative procedure to converge your solution. Okay, there has to be. So, after calculating L, calculate W nu as 1.2 times L. Calculate W nu as 1.2 times L. And using that W nu, now pay careful attention here. Using that W nu, recalculate epsilon Re nu or epsilon E nu. Okay, because what is going to be the testing parameter here? W can be anything, but W changes your dielectric constant fringing or effective dielectric constant. So that is very important parameter to design or you fix your length properly, because more the fringing, then lesser will be the actual length. So that needs to be judged. And on what parameter it depends? It depends upon epsilon Re or epsilon E effective, because it has a role to play over here, right? So you calculate W nu using 1.2 times L. You have calculated at the first step. Then use this W nu over here and calculate epsilon E nu. Then you need to check whether this is converging to the previous assumption, because you have done 50% assumption, right? So you need to check. So what you will do, you actually take a difference, mod difference, absolute difference of epsilon E nu minus epsilon E. Mod difference of epsilon E nu obtained at the second step and the first one, assumption epsilon E, if that mod value is less than or equal to 0.02. If that mod value is less than or equal to 0.02, the values of L and W obtained at the end of first iteration are your design values. Again I repeat, if the difference epsilon E nu minus epsilon E, which you have calculated in the first iteration, in the first approximation, if that difference is less than 0.02 or 2% error you are considering in the values of epsilon Re, then the design values of L and W obtained at the end of first step are your MSA rectangular patch dimensions. If that doesn't happen, then the next step, using this epsilon Re nu, you recalculate Le, that is Le nu. F naught is there, epsilon Re nu have to be used over here and recalculate Le nu. Okay, recalculate Le nu and then using this equation calculate L nu. For calculating this delta L, you are going to use nu epsilon E over here that you have obtained at the second iteration. Okay, so you calculated L nu. After that, you calculate W nu 2, that is 1.2 times L nu. Okay, the third iteration now comes 1.2 times L nu. After calculating that W nu 2, recalculate epsilon E nu 2. Recalculate epsilon E nu 2. Why? Because W had changed. Then after calculating that, see the variation in nu epsilon Re, that is epsilon E nu 2 minus epsilon E nu 1, calculated in the second iteration, not the first one. If that difference is less than 0.02, then your design parameters obtained at the end of second iteration now are your RMSA design values. Okay, this is the iterative procedure. Generally, within second iteration or in some of the cases first iteration itself, you calculate the values of L and W. Okay, so this is the iterative procedure which is there. Okay, iterative procedure have to be applied for checking this nu. Why? Because that is the fringing parameter that decides your fringing length, that decide ultimately your length of the patch. So, and why? Initial approximation we have only done for that only. So that is the assessment parameter. Whether that is converging, when we are saying less than 0.02 means what? We are saying whether that value is converging. So that convergence we are checking after making some approximation and doing couple of iterations. Within maximum couple of iterations, your solution is achieved. And when you design the antenna, a rectangular patch, using this iterative procedure, you are very close. When you simulate that using i3D, CST or whatever software, and when you fabricate that, your frequency of operation, what you aspire for, will be as per the value which you design. So 900 megas, maybe 920 or 880, you will get as the design value. That much close this procedure is. So here I have explained for 1-0 mode. 0-1 के लिए क्या होगा? Here 0-1 for 0-1 mode, if I want to design for 0-1 mode, W will get replaced by L. Here W will get replaced by L. You will calculate epsilon E for that. Procedure remains the same. Then here this will go, but this will be present. Here it will be WE you are going to calculate and then use this equation. Then L nu you will calculate as 1.2 times W. Using that, calculate epsilon nu by using nu L. Only the interchange of W and L will take place to use this procedure to calculate the RMSA dimension operating at 0-1 mode for the given frequency. Okay, so this is the procedure to design a rectangular microstrip antenna at 1-0 mode or 0-1 mode. Generally, we don't talk about the design procedure at higher order modes. The reason is they do not offer broadside pattern. Okay, higher order modes have different role to play. That we will see later in few of my next lectures. How the higher order modes to be assessed, why they should be assessed, because they have very significant importance with respect to the design of dual band antenna, multiband antenna, broadband antenna, even in the defected ground plane structures. So higher order modes we'll discuss later. Okay, but generally we design your antenna, let it be a circular, let it be a rectangular or equilateral triangular, for the fundamental mode of operation where broadside response is obtained. Okay, that is the lowest cutoff frequency of your antenna. Okay, so this is how we design a rectangular patch. Fine. So we have designed it. Now we should know the procedure, because once we have designed it, we need to find out where the feed to be located. Antenna to ho gaya. We have calculated L and W, but now we should know where the feed should be located. Now earlier I have mentioned selection of W against L is very important. I have already told you W is taken as 1.2 L. It is basically from the gain. If W is less than L, that is the length, aperture area is small, antenna gain reduces. But if I take W much larger than L, maybe more than 1.5, then you will observe that the 0-2 mode frequency comes very closer to the 1-0 mode frequency. 0-2 mode frequency it comes very closer to the 010 mode frequency at which you have designed your antenna. This what happens, this is the 02 mode field distribution for the fundamental mode excitation, because this is the field distribution you will excite 10 mode. But the same feed point will excite 02 mode. क्या होगा 02 में? You will have zero variation along length of the patch, but 2 half wavelength variation along width of the patch. That is what is shown over here. And for the feed point location, see, no matter what you do, for any feed point location which excite 10 mode, always excite only 10 mode to be precise, you will always excite 02 mode. So that 02 mode placement plays a role in the cross polar design. Unnecessary, rather if you just go on increasing W, this field distribution will interfere with the field distribution of 10. So the current distribution purity, the pattern purity will be lost. Of course, gain can increase, but it will drop down, because why? The orthogonal contribution is coming. So W cannot be much larger than L. It should not be more than 1.5. In fact, in all reported broadband antennas, they take W to be more than L. Why? Because all the higher order modes are closely packed. Then it becomes very easy to tune them with respect to the fundamental mode. But that is a different design aspect. Okay? From understanding point of view, from the fundamentals point of view, W should be less than 1.5 L. So we take around 1.2 L. That is the fair good of value. In square microstrip antenna, we take it that in the range of W is equal to L. From circular polarized antenna, realizing a rectangular patch, we use nearly square antenna. W is nearly equal to L. W can be 1.05 times L, 1.1 times L. That way we design this W and L. Okay, so selection of W I have explained the procedure for calculating the dimensions of the antenna. Why this iterative procedure? That everything should be known to you. Why iterative procedure? Why we are checking the convergence with respect to epsilon Re? That is something very, very important. Okay, fine. Now, once the antenna is designed, and this is just the prototype. We have explained this. Once antenna is designed, now we should know where to feed it. Okay, of course, in the laboratory purpose, we are going to use a coaxial feed. So you should know where to put that feed point. Okay, in the microstrip antenna, there is a half wavelength variation, and when there is a feed over here, this edge is positive, this edge is negative. Okay, current is this way, current is maximum in the center and minimum towards the edges. Impedance plot will be following the voltage plot. Okay, so impedance, since the current is maximum, impedance will be 0 here. As it is an open circuit over here, impedance will be maximum here. Okay, impedance will be maximum here. Here, impedance is maximum, but it has not gone negative maximum. Why? Current voltage polarity has reduced, but the current is in the same direction. So the impedance is maximum, but it will be like this. See, the plot will be like this. Sorry. The plot will be like this. So the impedance plot will look like this. It will not be negative. Current is decreasing and the field is reversing the polarity. That's it. So we need to design somewhere, because somewhere here you will get 50 ohm point. Somewhere there you will get 50 ohm point. So that X location where the 50 ohm point is there is obtained using this equation. Okay. Re is the impedance of the rectangular microstrip antenna have these two slots, because as we have said earlier, there are two radiating slots. Those slots are representing the radiation, so they are having some impedance, because ultimately dissipate hoga na energy. So that radiation is represented in terms of slots or radiating slots or the resistance. So this is Re is towards the edges, that is the resistance towards the edges, Why we are not considering these A resistances? Because we know at fundamental 1-0 mode they are not contributing. Hence, these two RE is only considered. So RE is the effective radiating slot which is there on either side with respect to this coaxial field location. Okay, so RE is there, X is you want to find out, L you have already obtained. There are formulas for RE. GR is the radiation conductance, okay, for a slot, and GM is the mutual conductance arising because of two slots. Why? Because there are two slots, right? Separated by a distance of lambda by 2. So there is going to be a mutual coupling. So that is GM is the mutual conductance. But for distance when it is equal to lambda by 2, GM value tends to be 0. Hence in the calculation we generally do not take GM. Otherwise, to be more precise, we have to take that. But since the length of the patch is lambda by 2 in length, we can neglect it because GM is very minor contribution. So you only have 2 GR. There are formulas which are there in the book, okay, in the literature. Once the dimensions are calculated, L and W, once the dielectric parameters are known, in terms of those parameters, you have formulas to calculate GR or RR or RE basically, and then from that X can be calculated. Okay, so this is how you can calculate the feed point location X for say a 50 ohm point or a 60 ohm point. Okay, this is how you do the impedance matching of the rectangular microstrip antenna using coaxial feed. Remember, using coaxial feed. Why? Because you are using a coaxial feed over here. Fine. So this is related design ho gaya. We have done the impedance matching. There are formulas, and based on this you need to solve a sum. Okay. So the sum will be like this. Design the earlier one which I have given you. Design rectangular microstrip antenna on FR4 substrate in fundamental TM10 mode at 900 MHz. Then locate the impedance point for excitation of 10 mode. So you have to show the 10 mode appropriately and calculate the feed point location X for 60 ohm input impedance. So this is 60 ohm, L is known, you have to find out X, RE can be found out from these formulas. So this is how you do the input impedance matching for the rectangular microstrip antenna, or you can design a rectangular microstrip patch for the given frequency for the given impedance matching location. Okay, so this completes our design of the rectangular patch, okay, for the given location. Now array के लिए use है क्या? No, it is not used in arrays. Now we will see how the microstrip line feed designs are done, which are especially used in antenna arrays, or when you want to do the integration of microwave integrated circuits with the antennas. So that now we'll proceed to. This is just the design which I have told you earlier, a design plot in I3D. Okay, this is the current distribution I have shown you earlier. This is how, okay, this is how the switch chart looks when you design a rectangular microstrip antenna. Remember, microstrip antenna is a parallel resonant circuit. Okay, and this what we have plotted it on is a Z Smith chart. But if you see the Y Smith chart of that, in fact I must have told you in the RF circuit design course, okay, the Y Smith chart has constant G circles like this. So this locus of the rectangular microstrip antenna frequency plot is similar to the plot of parallel resonant circuit having R, L and C plotted on the equivalent Z Y Smith chart. If you recall, the Y Smith chart will have circles like this, concentric circles, which are mirror image of your Z Smith chart circles with respect to the center point. So these locals move along that constant R. That is the parallel resonant circuit equivalent R of the rectangular microstrip antenna. And if you see the impedance locus of this the resonance plot look like this. This is what R plus JX variation plot of your rectangular microstrip antenna. Remember, I have told you earlier, a driven modes we are considering. When the feed point location is fixed, the resonant modes to be assessed, and for that you see R plus JX curve. Remember, resonance is a circuit phenomena, then the power effects are coming. So resonance condition of the microstrip antenna have to be judged only from the R plus JX curve. Power comes later in the picture when the impedance matching mismatching take place. So you will see, since it is a parallel resonant circuit, at the resonance frequency, real part has a maximum value. Okay, and then imaginary goes to 0 where real is maximum. Slight deviation in that may happen if you are using a thicker probe. Then this 0 point may not coincide with the 0 of the imaginary. That will happen in thicker substrate. But the resonance condition will be the one where R curve, real part of the impedance, is peaking or maximum. Okay, this is the resonant circuit equivalent of your microstrip antenna patch. This is the 3D plot distribution of the antenna. This is the broadside one. This is the antenna plane, and this is the radiation pattern. If we, 2D pattern plots are basically the cuts, 2D cuts in the respective coordinate axis. Okay. As I mentioned earlier, 2D cuts in the respective coordinate axis will look like this. This we already discussed. Okay. Now this is very important. Now we will discuss how a microstrip antenna can be fed using microstrip line. First way of doing it is the one which is shown in the leftmost diagram. Here you have already calculated X, where you want to do the feed point using that impedance formula. Okay, so X is known. Just connect a 50 ohm microstrip line or whatever value as per your Zin equation or Rin equation which you want to find. If I want to match it to 60 ohm, just calculate this microstrip line width with respect to that impedance and then directly connect a microstrip line over here. That gives you the microstrip line fed rectangular patch for the given impedance. Directly you feed it over there. Okay, means what? X you have calculated for a given impedance. That given impedance, microstrip line width you are going to decide. Given impedance, microstrip line width you are going to decide. There are formulas. So directly go to your Google or whatever. Calculate the microstrip line width for the desired impedance on the given substrate and then directly feed over here. As simple as that. But the disadvantage is, here you are feeding although for this length, but here you are feeding along the width also. And that also leads to the excitation of 0-1 mode. Remember, for 1-0 mode, it has to be excited along x-axis only. It has to be excited along x-axis only. But we cannot put this, rather impedance point, we cannot directly locate because this impedance point of 60 ohm, 50 ohm is residing over here. And there is no direct axis over there where I can put my microstrip line. I can place it along the length at the bottom, but I cannot have a direct axis over there because W is coming in between. So here I cannot put this same input impedance line, microstrip line over here because it will lead to a mismatch, because this is the open circuit. Edge impedance of the microstrip line is Re, which you have seen it in the previous formula. So Zin is not equal to Re. So I cannot put this microstrip line which you have designed for the given impedance over here. And that's why this method cannot be used by avoiding orthogonal mode excitation. Also orthogonal mode 0-1 mode also will get partially excited. So I cannot use this microstrip line, although it is a simpler one. If you have W very small than L, this method will work. If you have W very smaller than L, this method will work. Why? Because orthogonal mode frequency is very high. or 0-1 mode frequency is very high. But if W and L are comparable, then your impedance matching technique using this will not work. In fact, the question can be asked this way: discuss various microstrip line fade technique of microrectangular patch. So this is how you have to explain advantages and disadvantages. Like the one we have done it in feeding technique of microstrip antenna, coaxial to microstrip line to electromagnetic to aperture. So jumping from one to another, why it was done? There was a reasoning. Similarly over here, there has to be a reasoning. Why we cannot go from this? Because this appears to be the simple logical solution. But we cannot use this because of the orthogonal mode excitation. So what is that? We go to a next type, and definitely we cannot put it over here because impedance mismatching occurs. Hence we go to the next type, inset microstrip line feed. Inset microstrip line feed. What we do over there, we cut a slot. We cut a slot along the length of the patch. Okay, when you are cutting the slot along length of the patch, it does not affect 1-0 mode frequency. It may have its effect on 0-1 mode frequency, but that we are not bothered about at this moment of time. Why? We are working on 1-0 mode. So we cut a narrow slit, I will say, along the length of the patch, and we take our microstrip line feed of Zin value, Zin impedance, to the point where Zin exists in the patch. कहाँ पे Zin existed है? इधर है, not over here. So we cut a small slit inside that, and we take our strip line inside to that point. How much should be the slot width? Maybe W plus 2 mm on either side. W is width of the microstrip line of say 50 ohm or 60 ohm as per your calculation. So we take it inside over here and feed it. In this method, we are directly pointing towards the 50 ohm or 60 ohm as per your calculation. We are directly pointing towards that. Plus, we are not exciting orthogonal mode because we are feeding it right in the center of the width along the length. Okay? But the only disadvantage is this: it is more complicated compared to the previous one. You need to precisely calculate that location, cut a slot and take your line there. But if you see in array designs, this is heavily used. Inset microstrip line feed. I can use it in the same concept. Can be used in circular patch also for given impedance matching, or even in equilateral triangular patch also. It is not that only rectangular patch this is to be used. I can use in any regular shape antenna operating in its fundamental mode. The only care what you have to take is it should not affect that frequency, the fundamental mode frequency at which you are designing your system. Okay, so this is how you do your rectangular microstrip antenna inset feed design. Inset, why inset? You are cutting a slot, you are taking your strip line inside the rectangular structure and feeding it. Okay, the name. But what is the disadvantages? Bit complicated mathematically. थोड़ा काम करना पड़ेगा, and then only you will be able to do this matching, but heavily used. The last variation is quarter wave transformer microstrip line feeding. Now why it is required? Here we have seen the impedance is very high. So directly ये line में I cannot put it over here to realize the impedance matching, because वहाँ पे आ रही है, मुझे Zin चाहिए, 50 ohm चाहिए, 60 ohm चाहिए. So what I do, I use a quarter wave transformer. You have seen in transmission line, quarter wave sections of the transmission line or the microstrip lines can be used for the impedance matching. Means what? If this is the line section, here you require Z0. That is the required impedance. Here you have edge impedance of the microstrip line. Then under root this into this value, that is Z0 into ZL, so RE gives you the characteristic impedance of this line, which gives the impedance transformation. This is your formula of quarter wave transformer. You have an input impedance equation of a transmission line. In that, put L is equal to lambda by 4, you will get that equation. So this is what is written over here. I want 50 ohm on this side, RE is the value over here, length equals lambda by 4. Which lambda by 4? Lambda by 4 at the resonance frequency of my rectangular patch. Then I calculate Z0, that is the characteristic impedance of the microstrip line, which is used for quarter wavelength section matching. Okay, so again, no inset is required. You are not digging into the patch, so you are not affecting directly 01 mode frequency. I am not matching for 01, but I am not affecting, because when you cut a patch lot over here, it affects 01 mode frequency, it reduces. Sometimes that is not desirable. So here it avoids this. But what is the disadvantage? It is a frequency dependent. Why? Only at one frequency where this length is equal to lambda by 4, it provides that transformation. Still better, not bad, but not optimum with respect to the broadband design. Not optimum with respect to the broadband design. So we have discussed 3 different types of microstrip line feeding techniques used in rectangular patch. Same concept can be expanded with a similar discussion for the circular patch, equilateral triangular patch, or even any other irregular shape geometries, where you should take a care that orthogonal mode frequencies are not getting affected, or they are not excited also, because your role is to design the antenna for the given fundamental mode frequency. Okay, so this is all about microstrip line feeding. This is the example of a microstrip line feeding technique. This is a patch, the line width is calculated as per the edge impedance, and then you can have a side wave excitation as required in MIC circuits. Okay, this is the impedance plot. Why earlier it was this way, why it has become this way? Because the reason is because this additional length adds to the inductive effect, J omega L. So that causes the rotation in the Smith chart. Okay, this is one such fabricated prototype of microstrip line fed design. A side wave edge connectors can be used. Okay, these are already discussed. What is the effect of 0-2 mode? Okay, so here now we have concluded your rectangular patch design. Okay, we are concluded your rectangular patch design. Now we have to start with, I'll give an introduction and I'll explain the design procedure for the circular microstrip antenna. Okay, and then we'll stop for today. Equilateral triangular patch, we will take it in the next lecture. Okay. Now we'll start with the design of circular microstrip antenna. Now, as the name suggests, circular is the radiating shape. So, a name circular microstrip antenna. The resonant frequency equation for the circular microstrip antenna is given over there. K and M are the roots of the kth type Bessel function of nth order, and mth root we are taking. So, K and M is the mth root of nth order k type Bessel function. Okay, when we actually go to, you will learn that in microwave engineering. When we talk about a rectangular waveguide, we talk about these sinusoidal functions, sine and cosine. When we talk about the circular waveguides, we consider these Bessel functions. They are basically Bessel functions for application to circular cavities. Okay, so Bessel functions roots are used for fundamental mode. K and M equals K11 is equal to 1.84118. Directly those values are available in the book. Now fundamental mode in circular microstrip antenna is TM11. First N stands for one wavelength variation along the complete perimeter, or one half wavelength variation along half of the perimeter. The way you look at it. One stands for one wavelength variation along the complete perimeter or one half wavelength variation along the half of the perimeter. And second one stands for one half wavelength variation along the radius. So this is how the field distribution for the fundamental TM11 mode looks like. In fact, there is an analogy or comparison or similarity with respect to the 1-1 mode distribution of circular patch as well as 1-0 mode distribution of the rectangular patch. Okay, so this is the fundamental mode of the circular microstrip antenna. Now what happens is, if you look at this equation, A is also variable, epsilon E also variable. So if I want to find out the patch radius, because ultimately you have to find out the patch radius, and the resonant dimension which is present in the circular patch is the patch radius. There are no like W and L over here which decide the frequency. So only one resonant dimension is there, that is the patch radius, AE. So if A is also variable, epsilon R is also variable, because all along the perimeter of the patch the fringing is going to take place, like which was seen in the rectangular patch. And that estimation of AE while considering fringing effect is a complex procedure. What is this equation is, what they actually calculate is the capacitance of the circular disc when the dielectric material is there and the air is there for the same thickness. And based on that, epsilon E is calculated. It is the ratio of the two capacitance. So it is more involved procedure, because I cannot directly use this equation for calculating the resonance frequency, or calculating the radius for the given resonance frequency, because ultimately from the design perspective that equation should be available. But here you have two independent variables. In the RMSA also it was there, but we have done some approximation. That approximation is not fully possible here. And the effective dielectric constant is basically the ratio of two capacitances. So it's more involved procedure. And in fact, then effective radius also you will see lot of big formulas are there. So to calculate given radius for the given fundamental mode frequency, based on this only some simple formula was derived, and this is the formula for circular microstrip antenna operating at fundamental 1-1 mode. Okay, in fact this formula has come from the previous formula only. When you actually substitute and try to relocate the terms in that formula, you will see that it is the same formula. So here FR you substitute in gigahertz. Okay, FR you substitute in gigahertz, epsilon RE as per your design, K value which you will get, you substitute over here. Don't worry about its unit. H you substitute in centimeter, okay, H everywhere, and then value of A, what you get is in centimeter. So you have to be very specific about these units here. FR put in gigahertz, then take the value of K calculated from the first equation, take H in centimeter, calculate A. This is how you design a circular microstrip antenna operating at fundamental 1-1 mode. So the same problem statement can be extended to design a circular microstrip antenna at a given fundamental TM11 mode frequency of operation. Right? So this is a design equation, or rather I will say synthesis equation, that was the analysis equation. Okay. Earlier equation can be used where radius is given, find out the frequency. Because once the radius is given, using that capacitance formula, one can find out what is epsilon E and then calculate frequency. But that is not really useful for calculating the radius for the given frequency. The second formula which I have shown you is used. Okay, so this is about circular microstrip antenna fundamental mode frequency as well as the calculation of that. Now we'll just see which is the higher order mode. TM21 is the higher order mode. Of course, there is no linkage of that. Okay, here 2-1 means 2 wavelength variation along the perimeter or 2 half wavelength variation along half of the perimeter and 1 half wavelength variation along the diameter. But if you see here, this is positive, in the center it will be 0, this is positive. So the variation of half wavelength is not changing the polarity across two ends of the diameter. That is the specific property or peculiarity of the Bessel function, because of which this kind of a half wavelength, the half wavelength variation is like this, plus to 0 to plus. This is coming from the Bessel function. Why this? Because ultimately it should be plus 0 minus like the previous one, but that doesn't happen. That is because of the Bessel function type or distribution. But it is half wavelength in nature. So TM21 is the next resonant mode. Okay, again the E plane is the plane which contains E plane vector, so it is along XZ, H plane is YZ. Okay, because of this radiation pattern is broadside. Very important advantage of the circular microstrip antenna against the rectangular microstrip antenna is the harmonic separation. Now I will explain you that term, what exactly the harmonic separation is. What happens is, your design antenna, you are fed to the source. Source is operating at a given mode frequency at which you have set, but it always, because inside a source there are frequency multipliers, oscillators or whatever. So at the output of the source, apart from the fundamental mode frequency where you have tuned your source to give output, your higher order modes also are operated. That 1 GHz, 2 GHz and 3 GHz so on. If you design at 900 MHz, 900, 1800, 2700, all those will be available. In rectangular microstrip antenna, your fundamental and higher order modes are in harmonic relation. So the fundamental mode is 900, next comes at 1800, likewise. So if you are tuned, if you are designing, if you are operating your rectangular patch at 900 MHz, then unknowingly you are also exciting your rectangular patch at 1800, 2700, maybe partially, but unknowingly you are exciting, because source frequency is there, although you have set it, that residual component is coming and the antenna is also operating. So that separation to the harmonic frequency is not possible. In case of circular microstrip antenna, KNN decides your relation between the fundamental and higher order modes. At fundamental mode, KNN is 1.84118. KNM at the next mode, that is 2.1, is 3.4118, 3.4 something. If you take the ratio of that, it is not a harmonic progression. 1:2, it is not there. So even if you design a circular microstrip antenna at 900 MHz, the next mode frequency TM21 is not double the frequency of the first one. Maybe it is around 1500, 1600. So that harmonic separation for the next higher order mode frequencies is given by the circular patch against the rectangular patch. Of course, when we cover equilateral triangular geometry later, we will have a comparison of all three. We will have a comparison of all three, but this is the main advantage of the circular microstrip antenna. It provides you the harmonic separation. Okay, so we have talked about circular microstrip antenna, we have talked about its radiation pattern, the impedance matching. There are no direct formulas which are available, but again, if one can design, it can lead to some kind of a conference or conference publication that we can come up with some closed form equations by having its comparative study with respect to the rectangular equation to come up with the equation for X for a given input impedance location for a circular geometry. Also one can design that. Otherwise, generally for a 50 ohm matching on FR4 substrate, value of X is taken around A by 2. A is the patch radius. Around A by 2 it works on FR4. Other substrate it varies by loss tangent varies. Okay, so this is the free, current distribution. You will see this is the field location. Field is positive here, maximum positive. So you can see a comparative analogy between the TM10 mode distribution and 1 mode distribution. In fact, this part can be treated as constant and this part can be treated as a varying field. And using that concept only, in the literature, there have been the resonance frequency equation of rectangular patch obtained from circular patch or circular patch obtained from rectangular patch. Why? Because of the current distribution similarity. Okay? This is the Smith chart, as I have already told you, for rectangular geometry. So this is this we complete your rectangular patch also. In the next lecture, we will start with the design, the last part of the regular shape geometries, and then we will touch upon, because some of the irregular shape geometries of the circular patch I have mentioned here, but this we will take up after covering the equilateral triangular structure, and then I will talk about some of the modified variations, as well as we will have a comparison of the rectangular geometry, circular geometry and the equilateral triangular geometry, and some of the modified shapes which we will take up later. Then that will complete our introduction topic of the microstrip antenna design. So next lecture we will meet and we'll start with the topic of equilateral triangular microstrip antenna design. So here we complete your RMSA as well as CMSA. Okay, thank you.